All right. Good morning, everybody, or afternoon, or evening, depending on the place you might be. I'm Phil Wagstrom with the Office of CTO here at Vast Data. Welcome to our webinar. We're going to be talking about the Vast platform as a whole. We're going to go through the Dase architecture a bit here today and talk about how we do things internally within Vast. So I appreciate your time here. Please feel free to ask questions in Q&A. We do have folks that will be able to answer those. But with that, let's get started here with that. For the next hour, we'll go through a bunch of good information and teach you a little bit more about the Vast data platform. I'll go through, share out my screen, and we will get started here. All right. So we are going to talk about the Vast data platform. We're going to be talking about the Dase architecture. So first off, let's go through and let's start out with what is the Vast data platform. So we are Vast data. We are not Vast storage. We are so much more than storage. The goal of Vast data is that we want to be able to go through and make use of all the data that we have there, not just be able to store it, but want to be able to actually make use of it. This includes not only the data itself, files, objects, database tables, things like that, but all the metadata around it as well. So, the catalogs, the components of this, any tags you might have for various things. And we're going to be able to incorporate all those with codes and triggers to make your pipelines more efficient, whether they be AI pipelines or life science pipelines or analysis pipelines. Put all of that together with codes and triggers. So this includes, three fundamental parts. We're talking about the Vast data store. The data store itself is your traditional NAS storage. So we support NFS, SMB, S3, all the traditional ones there. We also support various different access methods for these here, supporting different workloads, not only your unstructured data, but also things like VMs and containers, all that good stuff. And then we also have with this the Vast database, which is a transactional warehouse for the data here. And we've got some examples of this. Our Kafka implementation actually makes use of the back end of the Vast database included with it. But we can go through and leverage that as well. Now, kind of a hybrid of this is what we refer to as the Vast catalog, where we can actually go through and index your unstructured data, take all that good metadata on it, their S3 tags, the file sizes, the owners, things like that, and incorporate that into a database, which we can then go through and search and have access to all of your information in a very easy to use platform. And then along with that too, we have what's referred to as the data engine, which is where we'll be able to go through and put all of the code with that, all the triggers and context of that data when it lands on the platform. That is what's referred to as the data engine. So let's talk about the Vast architecture itself. And Vast architecture has what we refer to as Dase, which is disaggregated shared everything. This is a much different architecture, a newer architecture for there, which seeks to go through and resolve some of the trade-offs that we've had to go through and make in the industry for years and years and years. You typically would have to go through and make trade-offs between high performance and capacity with multiple tiers of storage, whether it be your hard drives or your SSDs or caching things locally. And the goal of Vast here is to go through and have a single platform to break all of those tiers, where you no longer have to make the trade-offs between, do I have high performance and large capacity together. That is what we are here to go through and seek or to go through and break those barriers, where you don't have to make those decisions. You can get high performance and high capacity throughout with all of the data without having to go through and migrate things around complex mechanisms. So kind of the problems with the older architectures there, the scale up and the scale out and the parallel file system, they all break down at some point. Scale up, you wind up having, those wind up being larger and larger systems for that. Eventually they get to a point where they become very unwieldy. It's a large frame that's there, and if the one frame goes down, that's a pretty big blast radius for data unavailability. And then you have scale out, which is more your shared nothing architecture, and those solve some other problems there where we can go through and grow out with that. But they start to break down because each individual component of the scale out architecture may not have visibility to the entirety of the availability or the entirety of the storage there. So that causes problems when we start looking at things like data reduction. It also causes issues once we start talking about being able to get keeping everything in sync. If we make modifications on one node, does another node see it? So there's limits with the scale out architecture. And then you have parallel file systems. And parallel file systems, again, those solve another problem, but they're complex, they're unwieldy to manage. Sometimes they lack some of the enterprise features with that, so they're not always the greatest solution. I mean, all of these solutions do work in certain environments, but they all have their pros and cons with it. The biggest one here, we're talking about a shared nothing system, is that with each one of these nodes that are out there, you wind up having a lot of east-west traffic that happens with them. So if I have a client that's coming through and accessing data off of that, we may come and hit one node, and that one node has some of the data, but not some of the other data, so it has to be referred to another node, and then there has to be traffic back because the client's only connecting to one of them, and you wind up having all this east-west traffic. And once you get to a certain point, you're spending all the time trying to coordinate between the nodes and not really doing any work. So there are some very big limits with shared nothing systems. Now, what VAST has gone through and done is that we've decoupled the storage from the compute side of this into this what we refer to as the Dase architecture. And at a very high level, the Dase architecture is broken up into a couple different components. We have our controllers, our controllers, which refer to as C nodes on the front end. These are our compute nodes for this. They are stateless. They are only responsible for handling the protocol aspects. So your NFS traffic, your SMB traffic, your S3 traffic, your database traffic. And in the back end here, we have our data plane, which are referred to as VAST-D nodes, where this is going to be your flash, where you have your components that consist of high capacity flash along with high endurance flash or SCM for this, and this is where the data actually gets stored. And there's going to be a high-speed fabric between all of these. Typically, it's going to be 400 gig Ethernet or InfiniBand, but there's going to be a high-speed NVMe fabric over this. The great thing about this architecture is that we can go through and scale these independently for this. We can add more compute if we need more compute. We can add more capacity if we need more capacity. And all of the C nodes here have access to all of the data in the back end as we go through and grow. So this gives us a lot of flexibility. So let's dig into that a little bit and some of the advantages. So one of the biggest advantages here is that, as I said, scale. Where we can go through, we can start talking about scale on these, where we would have here in a typical rack, we've got our C boxes or our C nodes up here. We may have our D boxes here or our data boxes here. There's a graphical example of what a D box might go through and look like. But we can go through and scale these not from within a single rack, within a single cluster. We can scale these across racks with multiple generations of hardware together in the same cluster to take advantage of all of that. And this can scale from a 1x1 to encompassing hundreds of nodes, both 100 C nodes and D nodes in the backend. So we can get very, very high clusters, very, very high performance clusters there. And the goal of going through and doing this and be able to include all of the different multiple generations of hardware is to get rid of or not have to do this refresh cycle, where the traditional model has always been that I buy a storage array and that will go through and have a certain life to it, and I get the next storage array, and you have to migrate data over from the old array to the new array and replace the old with the new. With VAST, you don't have to do that. We can bring in a new C nodes of different generations of hardware. We can add those C nodes and cycle out the old C nodes, add in new D boxes and cycle out the old D boxes, add as additional hardware and technology and performance comes available without having to go through that migration process where you'd have to maybe use something like rsync or robocopy or some other utility to go through and migrate data externally. We can do that all within the cluster without having to do that migration. So let's talk about, again, the benefits of a shared everything architecture is that we do have unlimited scaling. We can add additional compute, we can add additional storage in the back end. It gives us great resilience because these front end C nodes here are stateless, that they can be taken online and offline without having an impact to the cluster. We can survive a lot of failures of C nodes, or even when it comes to maintenance, when we're doing upgrades, we can do upgrades. We do upgrades in a transparent fashion where we do the upgrades online. Any C node can be taken out and added as we need to go through and do it. In the back end, here for the storage, we do have resiliency with those storage devices, and we'll talk about that, how we go through and do our data reduction and our efficiency with storage across the QLC devices. But we have resiliency with those as well, where if we do happen to lose a controller or a D node in the back end, we've got redundancy within those. So we've got a very highly resilient, highly scalable architecture and system. So what does this look like from a cluster hardware standpoint? What does this look like from kind of an architecture standpoint, a little bit more in detail? So this is your typical cluster configuration example that we have here for this. So in the front side here, we have what's referred to as a C box for this in this example. Now this architecture has kind of changed a little bit here, where the C box itself would typically be a quad server, but in terms of the architecture of a vast cluster, it doesn't necessarily have to be this quad server. That's not the building block here. It's actually these C nodes, where each one of those servers is going to be an individual C node. And I bring this up because there are with newer options that we have there, where the C node might just be a one rack unit server for use rather than these quad servers. So it depends on the hardware vendor that you're going through and utilizing. So we have our C box or our C nodes here in the front end. We have our D boxes. This gives us an example of what a D box might look like. This is our series style D box for this, with D nodes within those to handle the I/O to that. And then we have a set of switches in here. Now these switches here, this example shows a single pair of switches, but this could be any number of switches. It could be larger switches with more points. This could also be a high-speed switching network where we have a leaf spine architecture for that, with larger clusters if we're spanning across racks with big clusters. So, but conceptually, it's going to be a set of switches for redundancy with that. And when clients want to go through and connect up into the network, we'll support two different options, one of which is going to be a host connectivity, where the clients will connect up into your network or the customer's network via these internal switches. This and the clients here will connect to the C nodes and do via protocols of the C nodes. We'll be able to access data off of the D nodes there. The clients don't actually see the D nodes directly. For that, they're only going to be interfacing with the C nodes. The advantages of going through and doing this is that it gives you some simplicity in cabling. We're doing just switch to switch for that, so we can maybe use some less cable, consolidate some cabling there for that, but that's one connectivity option. Another connectivity option is that if we have these C nodes here where we're working, if the C nodes are configured with more than one NIC card in there, we can have a northbound connection, or a set of northbound connections, and a set of southbound connections, with what we see here, where each C node is individually connected up to the host network, to the client network, to your network for that, and the clients will go through and access things there. And then at the back end, the other NIC is going to be dedicated for the interconnect with that. Now, this here does give some other advantages to going through and doing it. You've got a little more flexibility with these C nodes. The C nodes can be all connected to the same physical network. They could be connected to different physical networks on that. They could even be using different networking technologies. So you may have some C nodes that are connected to, let's say, an InfiniBand network, other C nodes that are connected to an Ethernet network. So more flexibility with that. The downside of this, obviously, is that you have more connections that you need to have for the upstream side for that. So two different options. It depends upon what the use case is for those. And there again, there's different pros and cons with doing that, different flexibility with that that you wish to do. So let's talk about the hardware. So these are the two general D-box hardwares. Basically, a D-box is going to be a JBOF system. It's going to be just a bunch of flash. So we have options for either referred to as a Mavericks D-box or a Series D-box. The Mavericks D-box has 44 SSDs, going to be a traditional 2.5-inch form factor. These slide in from the sides for that. The series style D-box uses a ruler form factor SSD. The ruler form factor, you haven't seen these, are about that wide, and they wind up being about yay long. They're much longer and narrower for that. Series style D-box holds half as many SSDs as the Mavericks does, but it's also one rack unit rather than two rack units. So you can go through and do the math there from the capacity there. The different style of C nodes that are supported here, and these do vary depending upon what's available out there. But we do have, again, our traditional C box, which is a quad server here, 2 rack units high, or we now have the 1U C nodes as well for those. These are very common. These come from various different hardware vendors that are available, whether it be Dell or HP, or we know recently announced a relationship with Cisco for those, or Supermicro as well. So various different hardware vendors are providing these here. From an architecture standpoint, if we come back here to this is where our C boxes or C nodes would reside. This is where our D boxes would reside. And we do actually have another architecture here, which is another option for things. It has a little different method of doing things, but this is what effectively we get used when we're talking about having VAST on cloud, a cloud instance here, is that we have what's referred to as an E-box. So an E-box is a little bit different, where we have the C node personality and the D node personality within the same hardware platform. Used mostly for hyperscalers for that, but each one of those physical components contains a bit of both. The C node component is stateless still for that. So if that portion of it does have a problem, we can take that down, bring it back online. Obviously, because this is all in the same physical chassis, the loss of one of these does have an impact in terms of the availability of the SSDs in the back end. So the E-boxes, if we're using those, has different rules in terms of how we add things, specifically around when we're configuring a D-box or configuring a cluster that is E-boxes, and we want to expand or we want to establish one. There are limits, there are minimum requirements for the number of E-boxes to be able to maintain resiliency and redundancy in there. So you wouldn't be adding just create a cluster with just a single E-box. You'd be having a cluster with, let's say, 10 E-boxes or 20 E-boxes for that. You would be growing it in those kind of increments for there. But another different architecture for that. So again, the behavior is going to be very much the same. I mean, we still have the C nodes don't have to go through, and they're not necessarily communicating with each other. There is going to be traffic between the E-boxes, obviously, but it's going to be C node to D node, whether that be within the same E-box itself or going between different E-boxes there. So fundamentally, it is the same architecture, just different packaging for them. So then we've got some options here for this, and then we have some cloud instances here as well. So again, kind of the deployment options here from various different vendors. So let's walk into some of the Dase capabilities a little bit more here with this. So when we're talking about the Dase capabilities, let's look at how things are set up. So again, I've already kind of mentioned this where we're talking about the CPU generations, the different generations of hardware here. But again, we can scale asymmetrically on this here. So we can add different additional C boxes and C nodes into the cluster. We can add additional SSDs here. We can go through and we can add these in across different generations, all supported within the same cluster. So you can retire hardware on your schedule, not due to some forced retiring that we're going to go through and inquire. And the nice thing about this is that as we add in that additional work, those additional components, as we add in additional C boxes in the front end, be them the same architecture or newer generations of hardware, or we're adding in additional D boxes in the back end for this, the entire cluster can take advantage of all of that additional performance and functionality on it. So when we add an additional D boxes, they are the storage on those, the space available for those is available to all of the entirety of the cluster and the performance there. As we add additional CPU and C nodes on there, we scale the performance up for that. And we're not, effectively not concerned about the hardware that we have here for these here. It does, whether we're running a cluster or administering a cluster that has a single generation of CPU and D box in the back end, or multiple generations, or whether it's a cluster, a 1x1 cluster or a 100x100 cluster, it's going to be the same interface. It's managed exactly the same for those. So let's talk about when we want to go through and scale a cluster. So let's look at when we want to go through and scale VAST. If we want to go through and we want to scale additional performance, we need to have more IOPS on the front end for this. IOPS requires, on the network side, requires driving those packets in, requires more protocol overhead there. We can add additional C boxes, add additional C nodes for containers to get that performance for the amount of IOPS, the amount of throughput that we need, because that's where the networking is for those. If we need to go through, we need to add in additional capacity, we can add the additional capacity for the D boxes in the back end for that. So depending on what you need more performance, you add more C boxes, you need more capacity, you can add more D boxes. We can scale those. We do scale those independently. There are going to be some certain limits, scalability limits, in terms of the ratio of C boxes to D boxes. We're not going to support a single C box with 100 D boxes in the back end. There is overhead that it takes to go through and do management and handle those there. So there are limits with the scaling there. But in general, we can scale those asymmetrically. And again, we can scale this from the smallest cluster, about 200 terabytes, up to exabytes of storage, for these here. And as we go through and we add things, we get more capacity in terms of number of files and objects, and the resiliency actually goes up as we have more components in the cluster. So let's talk about how we can go through and how we can make use of some of these components. Because we've got all this performance, maybe I want to go through and I don't want to have everything available to everything, and I want to go through and segment things out. Well, how do we go through and put some capacity and some performance controls and some segmentation boundaries in here? And we do this through what we refer to as VAST server pools. And effectively, this winds up being done at the networking level. So when we go through and we create our access, we make use of what we refer to as VIP pools. And VIP pools are going to be a collection of IP addresses that will reside on a particular set of C nodes. Now, normally when we create a VIP pool, it's going to be across all of the C nodes. But if we want to, we can say, I only want this VIP pool to be part of certain C nodes or only reside on certain C nodes. And that could be for various different reasons. Let's say we've got a campus set up where we have two different networks. We've got a high-speed, we've got our high-performance computing network or a research network, which is separate from a general campus network. So we want to segment those out so that the I/O, the workload being done on the high performance computing side doesn't impact the campus network, or vice versa. So we can segment those out, dedicate those on specific C nodes on the front end for that. And again, these could also be different networking topologies. Either certain C nodes are connected to different physical networks, or different networking technologies, where we may have one that's InfiniBand based and another that is Ethernet based. Whenever we go through and we create our views or our export, even though the C nodes here have access to the entirety of the element store, when we create our views, and the view is a term that we use to cover the terms of an NFS export or an SMB share or an S3 bucket, we use the generic term views. When we go through and we create our views, we can specify for those views where the view is going to be visible. So we will only expose a view to a certain VIP pool, or we'll only have one VIP pool or multiple VIP pools. We have controls around that. Or even in the case there, if we want to go into the start talking about multi-tenancy, multi-tenancy is another option as well, where it gives us further isolation within the element store for these. But even if we're going through and we have these the data isolated, we're presenting things out, the performance of any one of those can take advantage of all of the hardware that's within the cluster. Within a VIP pool, the VIP pools are going to be used for client accessing. We're going to do some load balancing across those. With the VIP pool, we go through, we're going to assign IP addresses across these C nodes, and we'll be making use of, typically DNS to go through and do round robining across those. So every client that goes through and connects will get a different DNS IP address, get a different IP address, which will put it onto a different IP, which will spread it out across C nodes. The IP addresses here, when they are assigned to a C node, will stay on that C node unless there's a reason to move them in terms of, we maybe want to do maintenance, or there's a hardware failure or something where those VIP addresses need to move from one location to the other. For that. But the VIP addresses will reside on one particular C node for life of that. And clients, depending upon what the access is that you want to do, the clients, there's configuration options to have the client either use one IP address for just a single connection for that, or if we want to make use of things like multipathing and multi-channel and connect with all those options there, we can make use of those where a single client can connect up to multiple IP addresses and spread their workload across both of those, more C nodes than just one, to give us a nice even balance to be able to use as much of the performance in the cluster as we can without being limited by single links for that. So again, the VAST DNS, we do have a built-in DNS server for this. So as we create those VIP pools and we expand those VIP pools, we can have the VAST go through and divvy out those IP addresses in a way that gives us the best kind of load balancing that we can get for it. Now, VAST DNS service is not a hard and fast requirement. If you want to go through and just populate your upstream DNS with all of the IP addresses that are being used by the VIP pool, that's perfectly fine. But the advantages here of using the VAST DNS is that your typical upstream DNS server doesn't support a TTL of 0 directly. And we want a TTL of 0 so that when we have multiple clients starting up all at the same time, they're going to get different IP addresses resolved for that. So we don't have, basically a startup storm that all goes to one IP on one C node. It's nice and evenly balanced out across all of them. The other advantage of this is that as we go through and we expand the VIP pools, or maybe we want to grow those additional IP addresses, that will be reflected automatically for the VAST DNS service as well. Other options here too, if we decide rather than serving out a single IP address, we want to give out multiple IPs for a response, whether that be all of the IPs in the VIP pool or only a certain number of IPs in the VIP pool, the VAST DNS service understands how to do that. Very simple to go through and modify and allow that to happen. So another service, again, not a hard and fast requirements, but a vast majority of VAST customers go through and use this. Now, when looking at the internals of the platform, VAST is designed with multi-protocol in mind. That's been designed for the get-go. We don't use any protocol gateways. We don't dedicate certain C nodes to doing certain protocols. All C nodes are capable and do service out all protocols equally. Everything's authored in-house. VAST does maintain. We do write our own SMB stack and our S3 stack for that. We do maintain all of those in-house for those. But here we've got our protocol layer. These are all first-class citizens. They're all equally performant. For that, there's no inherent limitation, at least internally. There are obviously protocol differences between how an FSB3 and V4 work and things there. But from a VAST perspective, they're going to be equally performant. In the backend on the element store, we do have the data is stored in such a way that it is platform independent and protocol independent. The element store itself doesn't act like isn't a traditional file system by any means, so it doesn't have the overhead or the limitations of your typical of your traditional file systems. There, we're not trying to shoehorn things into POSIX mode bits or whatnot. We do store all the all of the permissioning in a protocol independent format. And the element store itself is more like an object store than anything else. But it does represent and present as a file system for those file system ones, or as an object store for S3, or as a database as we need to go through and make use of those. Some of the features here that the data platform has for these, and then some of the security options that we have for this. So we do support encryption in flight over NFS and S3. For those coming with the VAST 5.4 release, we're going to have SMB encryption as well. All the data that is at rest on the cluster is able to be encrypted at rest, either with an internal encryption key or an external key management. We support secure multi-tenancy, extensive auditing on the cluster as well for this, so we can audit any type of interaction across the protocol or administratively for those. Those can either be stored as files, JSON files that can be exported, or they can actually be imported or brought into the VAST database where they can be queried directly as well. Full ransomware-proof snapshots. Snapshots by definition are immutable, but ransomware-proof snapshots mean that we can't administratively delete those outside of a set schedule for those. So various different options for those there. All right, so let's talk about some of the internals here. We're going to talk a little bit about VMS for just a moment here. So the VAST data storage model here is that everything is API first. The GUI, the command line interface, the VCLI interface, these are all driven via the API. So if you're logged into a VAST cluster, you want to see the API calls that are being done through the GUI, you can call those up. You can look at, you can call up the inspect portion within your browser and actually see the API calls. We also have these extensively documented too. So off the platform itself, you can either append a /API or /docs to the URL for the VMS interface, and you'll be able to get the API documentation or a Swagger interface here to go through and see what is being done and even test out some commands there. But everything is API first. This allows us to go through an interface with various different modules, Prometheus and things of the such, to go through and automate all of the work that would need to be done for a cluster. We do have API documentation and databases, SDKs that are out there. If you go out to GitHub and look for VAST-data, you'll find our GitHub repositories, which has the various SDKs, not only just for VMS with the VAST Python SDK, but also for database and other things of such there. The clusters are able to be centrally managed. So if you have multiple clusters, we do have what we refer to as VAST uplink, where it's a cloud-based instance that will allow you to view all of your clusters from a single pane of glass. And if you want to go through and administer, it allows you to drill down to that local cluster and perform your administration locally on that cluster. The VAST platform gives us thousands upon thousands of metrics. The amount of metrics, these are collected continuously by VMS for this, and these will go down from either a very high level, just high level throughput on the cluster as whole, down to individual IP addresses, down to individual users, down to individual views, down to the individual NIC, and even down to the SSD. So we can get analytics there on pretty much whatever you're looking for this. These are typically turned on by default for this. There are very few analytics that are disabled by default, but all these are available for this. These can also be exported via Prometheus exporter to say like Grafana, or they can be queried directly if you want to get that data for those metrics available for it. And these, again, are going to be turned on by default. They're collected by VMS automatically. And then same thing for capacity management. You look at manage our capacity here, either from the cluster using the capacity estimate, which will give us our data reduction ratios. For this, we can also go through and make use of what we refer to as the VAST catalog. It allows us to query the cluster, query the element store to get information from it for that. Again, these are all API accessible for these. And then we have data flow. Data flow is great to be able to go through and look at. It's the first place to look whenever you're having a performance problem. Data flow allows us to to see, identify the individual user that is coming in, regardless of the host that they're logged into. So we'll see the user that's accessing, the host they are logged into there, which VIPs they are going through and coming in on, which C nodes that are going to, which views they're going to. So we can take this all in real time or historically and dig down to see where those are and how much I/O is going on here. Nice thing about it is that looking at this from the get-go, we can look at this little colored bar under any one of these and see, given the list that we have there, which one is doing the most amount of I/O or what percentage of I/O here. So looking at this here, I can see, it's kind of hard to see here. I would probably go through, find out who that vast user is that's doing work, and say, what are you doing on this that's using all this performance here, maybe causing other things there. And if we do have issues where we need to limit that, we have full quality of service there where we can go through and throttle those noisy neighbors, whether it be just on a view basis or on an individual user basis, and that expands not only to single protocol, but across all the protocols that user might be using. Okay, so let's move on a little bit here, talk about some of the data reduction capabilities that we have and how we lay that data out within the element store. So first off, let's talk about this here. So VAST has done a lot of work to go through and analyze the types of data patterns we use QLC Flash, and QLC Flash, if you're familiar with it, is not necessarily the most resilient Flash that's out there. It gives you a lot of capacity, but every time you go through the read write erase cycles, that it does put wear on those QLC devices there. So, but VAST has gone through and done extensive analysis on how we go through and write, where we go through and write, and how we do that right into that QLC. That we'll go through, and if the hardware is maintained under a support contract and the QLC fails, for that, we'll replace that QLC device for up to 10 years for that. We'll go through also here, and when we're kind of help with that a little bit, we're going to go through and we're going to use what we refer to as locally decodable erasure codes. So locally decodable erasure codes is we'll use that when we write data out, and this gives us the advantage on not having to use the traditional RAID 5, RAID 6, different RAID mechanisms on there, which are great. They work great for hard drives, been used in the industry for that. But when we start talking about larger scale systems with lots of devices there is a significant amount of overhead with the traditional RAID. Locally decodable erasure codes can get that overhead down to about 2.7%. While maintaining resiliency for that. And then we also have what's referred to as our data reduction here to go through and give even more efficiency with our data storage. So let's dig into each one of those. So first off, when we're going to go through and we're going to look at writing data out to this, VAST has within the D boxes a large amount of write buffer space. So the D boxes are composed of what we refer to as SCM, or storage class memory. For this, very resilient SSDs devices, and then we have the QLC devices there. With that large write buffer with those SCMs, we can do some intelligence with writing data out and what we do. Not only is it with writing data out, but also with the compression, the analysis of that, to go through and minimize when we have to go through and write and rewrite those QLC devices to extend that life. So when we go through and we're going to write data out, we're going to try to go through and put data that is generally of the same expected lifespan. So it's data that's expected to be there for a while. We're going to try to group those together and write those out together so that we're not going to have to go through and erase those and do a bunch of rewrites in the QLC. If we can go through that. And data that's going to be a short life, we're going to try to keep that in the SCM if we can for that. So when it comes down to data reduction, we're going to look here at a couple different options here. So we're going to talk here first about compression. We definitely do compression. Compression works great. Compression here is basically we're going to take a chunk of data and we're going to go through and try to look at things here. We're going to compress that down. That works great, but it depends upon where you're doing the compression. What your record size is, where you're doing your blocking on, where you're doing the compression on. So it's great. It gets fine-grained. It's fine-grained with that, but it winds up being kind of local, and there's limits to that. We also can do deduplication, And deduplication will take multiple blocks of the same identical blocks, put those together. That's great, but if you have small differences with the differences between the two, you can't deduplicate across those blocks. So there's limits to that too. VAST will introduce what's known as similarity reduction, where we can take this here and look at these data blocks and say, hey, these two blocks here are almost identical. They're very, very similar. If we factor out this one little point there, they are identical, so we can dedupe those together with that delta, and that's what happens here. Is that we can go through, we can leverage compression, we can leverage deduplication together, and get some very good data reduction numbers for this, even with data that has already been compressed or reduced by other means for this. So there's a lot of flexibility for that. And we can do this because the data is able, we do have that large SCM buffer, so that we have the ability to go through and take some more time to look at that and do these other CPU, a little more CPU calculation intensive workloads to go through and get this kind of compression. Well, let's talk about the erasure coding. So within VAST, again, I said we don't use RAID 5, we don't use RAID 6. With that, we use locally decoded erasure codes. And what these allow you to do is allow us to get very large stripes for the data there, while not having to trade off long rebuild times. So when you have a sufficient number of devices, we will make stripes when we write stripes out at 146 plus 4 devices. For this. If you try to do this with traditional RAID, you'd be like, oh, why do I want to do this? But this is the great thing about locally decoded erasure codes, is that when we have these large stripes, we only have to go through and read a quarter of the devices plus parity to reconstruct any component. Now, internally, when we go through and we do some planning for this, that reconstruction, we already take into account that reconstruction when we're looking at the available capacity in the cluster, so we don't have any hot spares that need to be concerned about there. That's already been factored in. But when we do have failures here, like in this example here, we've got a failure on this, the reconstruction only has to go through and read a quarter of the remaining devices plus parity to reconstruct that remaining block. And that remaining block, or that missing component, is then rebuilt. That's going to be rebuilt to available space within the cluster, and this will happen immediately for that. So it's very, very efficient. Gives us a lot of gives us very, very low overhead, while still being able to deliver a very high MTDL resilience there, as high as 60 million years for that. So very resilient way of managing things here. And if we are going through and looking at with multiple component failures, if we're looking at things like trying to get rack level resiliency for that, those are options we have available. We just tweak the algorithm a little bit to make sure we're not selecting more than a certain number of devices from particular racks. So we have this spread out across racks. So if a rack does happen to fail, we can survive that with sufficient number of D boxes available within the cluster. So very resilient, very high performant for that, with very, very low overhead. So let's continue. Let's talk real quick about failure handling, how VAST does failure handling internally for this. So if we're talking about within the VAST itself, all the data is protected. Doesn't matter when it comes in, how it comes in. All the data is protected. All the write's going to be atomic. Either a write happened or it didn't. We don't acknowledge a write to a client unless it's actually been written to storage. Any data that comes into the write buffers or the SCMs is going to be at the very least mirrored. Where prior to the VAST 5.1, it was mirrored between different physical SCMs, typically going to be in different drives or different D boxes. But with the newer systems there, we now are actually using erasure coding on those to give us better performance, as well as more capacity for those there. So we got capacity there, and then we've already talked about the SSDs internally for the QLC devices, how we go through and do those. Now, in terms of failure operation, let's talk a little kind of how a normal operation works for an IO. So we've got our client here. Client is going to go through and do an IO request. That's going to incur a DNS lookup. They're going to be assigned get an IP address. That's going to go to a C node. The C node, the client will do the request to the C node. The C node will locate the data it needs to have on the D node, and it will get what it needs either from the write buffer or from the backend storage. And this here, even though it's simplistic here, the data may be across different D nodes, across different D boxes in the backend. For that, for this example, we're just talking about a single D node there, but it will go through and read that and then get the reply back. Now, if there's a failure in the back end for these D nodes here, the D boxes do have dual D nodes in there. Normal operation is that a D node will handle the I/O for half of the devices. In there, it does see all the devices. So if there is a failure that would happen on one of those, the other D node takes over. But when we do have failures here, the cluster will detect that failure. Maybe there's a missed heartbeat or an I/O problem with that for that D node. But the C node will just go and talk to the other D node and get the data from the other D node there, and then return them. So the client is completely unaware of it. If we have a case where we have a C node failure, so the client is trying to go through and do access to an IO. The C node goes down, the cluster sees that. The VIP address will automatically move over to another C node. The client, all they see is they're going to see a typical, just a TCP blip. You have to do a TCP retransmit. They don't have to reconnect. They don't have to log in. It's just a TCP retransmit. They're going to might see a RARP that comes across in the network saying, hey, this MAC address or this IP address is a new MAC address, but it's all at the TCP layer, not at the session layer. They don't have to log back in. And so the client will continue on. So the question I typically get is, what do you mean they don't have to log back in? How does this C node know that this client has a state there? Well, anything that is state related for stateful protocols like NFS or NFS v4 or SMB, anything that's state related in terms of a client is logged in and established a session, or a client has an open on a file, any of those kind of actions that are stateful are going to be actually stored on the storage class memory that any C node can go through and see. What this means here is that for failovers, the client doesn't have to reconnect, because based on the session ID, the client is connecting up here and the ID that's there. The C node knows where to go through and look to get the state of that session, knows the state of those files from that, because that's stored outside of the C node itself. So it's transparent to the client. Client doesn't have to reconnect. This is also how we can leverage not having to do east-west traffic between C nodes, because what in the case we've got a different client talking to a different C node trying to access the same file. The C node goes through, looks at the SCMO, says, oh, hey, there's an open on that file already by this client. I can't open it. The other C node does it. And they can do that without having to talk to each other. The C nodes do not have to communicate east-west to each other. But in this case here, we have our failure that occurs on that. The C node, the VIP address fails over. For this, the client just sees a TCP or UDP layer drop reconnect for that, and everything is good. When the C node comes back online, the cluster brings it back up, and the VIP address will move back over. And it doesn't necessarily have to be the same VIP address that moves over. It might be a different VIP address on that C node, but we'll rebalance those IPs out across the C nodes to make them even for that. And the client sees basically the same thing. It's going to be a TCP drop reconnect at that layer instead. And this is very resilient here. This does not only apply to things like reads, but it applies to writes as well. The writes are a little more, there might be a little more of a delay there, because any writes that were in flight for this when a C node may have failed would have to be retried, but it's not going to be a catastrophic, like that. It's going to be handled like any other TCP reconnect, where the client just retries it and continues on for that, but without having to go through and log in. So with that is a very quick overview of the VAST architecture for that. We do have some questions that are out there that I'll try to go through and answer. Let me stop sharing my screen here. Stop sharing here. Let's take a look at some of those questions. Okay, so it looks like we got a question here for this. These will be recorded here. For physically smaller customer, so there's a question there talking about for physically smaller clusters, locations where Powell auditors can take down an entire rack. It's possible to change dbox protection, erasure coding ourselves while the cluster is online. So yes, you can enable dbox HA after the fact. It does allow for the ability to do that. You need to have a sufficient number of dboxes. The limitation today, I believe, is 8 or is it 10? I can remember the exact number there that we have limitation there. There are going to be trade-offs in terms of the data reduction rates, the capacity that you have, because again, we're going to be limiting, it limits not only the devices that we go through and take for a cluster when we're writing that erasure stripe out, but it also would effectively increase the overhead because we can't. We're still going to have those 4 parity devices, whether that stripe that is written out is 18 devices wide, or whether it's 146 devices wide, we still have four devices of resiliency. So it can be turned on after the fact for that to give us those kind of abilities there. All right. So with that, I don't see any other questions that are out there. Kristen, was there any other questions there? I see you've been able to join me.
The only thing we were talking about is making sure that we give the recording to you afterwards, so you guys will receive that. I'm going to put the topic for our next session in the chat. And also we have our registration pages ready. So I'm going to put that there too. So if that's of interest to you. So this webinar is going to be on automating fast storage operations. It's going to be some really cool new content with some new labs attached to it. So highly recommend you all attend. It's going to be led by our community director, Jonas Roslin. So with that, I think we can conclude our time for today. Thank you all very much for joining.
Thank you, folks. Have a good day.